Okay, so we know by Riemann how to approximate the areas underneath curves using rectangles. Now we are going to turn an approximation into an infinitely good approximation. So we're actually going to find the area underneath the curves. And so the whole idea here is if you have a curve, let's call it f of x. Then I can approximate the area underneath f of x up to a certain point. Let's say maybe there's b and here's a. Right, I can approximate the actual area by using rectangles. And the idea here is the more rectangles you use, the better your approximation becomes. It's like increasing the resolution on a photo. The more pixels you have, the better the quality of the image. Right. But now we're actually going to find the exact area because we're going to take this picture right here. So the area of that is going to depend on n, the number of rectangles that I use. So this is actually going to be a function of n. Actually, maybe let's call it not g of n, but a of n, because it gives me my area. And then I'm going to take that area equation and see where it goes as I send n to infinity. So as I get a better and better picture, as I use more and more rectangles. So this function here, x plus 1. So this is not too difficult of a function. In fact, it's a linear function. We're going to use some geometry later on to make sure that we did actually get the right area. So the area over the interval 0 to 5 of the function x plus 1 is no longer approximately equal to, but is going to, in fact, hold on. It is going to be approximately equal to a Riemann sum, which is going to be the sum of a bunch of rectangles. Bases are going to be b minus a over n, and the heights of the rectangles are going to be given to me by my function at points, and at which points? A plus b minus a over n times I, where I is the rectangle that I'm on. Let's use a right-hand Riemann sum. So just a quick word about this. If you've got a function, here's a. So the base of your rectangle is b minus a over n. So if you move over to a plus b minus a over n, then you moved over, that's your first rectangle. And that's, we're using a right-hand Riemann sum because I is starting at 1. So if I starts at 1, then the first function value that we actually take is a plus 1 rectangle width. So we actually do take this point as the height of that rectangle. You can use a left-hand Riemann sum too, but they're both going to give you the same answer. So let's use a right-hand Riemann sum. I think it's a little bit easier. All right. Okay, so this is an approximation, right? Because even though I don't know what n is, as long as n is a finite number, it's just going to be an approximation. But now, as I take the limit as n goes to infinity of the area, well, now it's no longer an approximation. It is the exact answer. Okay. So we need to take the limit at the end as n goes to infinity. Let's leave the sum alone. Let's tell ourselves what b minus a over n is. So that would be 5 minus 0 over n. And let's tell ourselves what happens if we plug, actually, let's not plug that into the function just yet. A is 0 plus b minus a over n times I. We already know that b minus a over n is 5 over n. So 5 over n plus I. In fact, even on my next step, I'm not going to tell myself what the function is. Right? The algebra here can get kind of messy. So you want to simplify as much as possible before you move on. For instance, that 5 minus 0 over n, let's just write that as 5 over n. And 0 plus 5i over n is just 5i over n. Okay, now let's tell ourselves what is the function value at 5 over n. So if you plug 5 over n into your function, you get, oh, sorry, 5i over n. You get 5i over n plus 1. Okay, let's see. The limit sign is still there. We will eventually send n to infinity. The sum of all of those rectangles. Let's distribute this 5i, sorry, the 5 over n. So you're going to get 25i over n squared plus a 5 over n. Okay, my goal here is to write the sum of I, or the sum of I squareds, because I know something about those. Right, that one was given to us by Gauss. Limit as n goes to infinity. The sum, and we're going to start that sum at, we're going to start at I is equal to 1. And actually, you know what? I want to write that as the sums of i's. So notice this sum right there depends on I. So anything that's not an I is just going to be a constant. So let's pull out the 25 over n squared. We're going to get limit as 25 over n squared times the sum, and I'm just left with the I in that sum. Right, this I right there. I'll add to that. Again, 5 over n, the sum doesn't know what to do with that. Just treats it as a constant. So now you've got a 1 as a placeholder there. Okay, let me borrow some space from the bottom here. Let's see. I can't bring the 25 over n squared past the limit because the limit depends on n. So the 25 over n squared is right there, but I can replace the sum of I. Oh, I didn't have it indexed. 1 to n with this equation here. The sum of I up to n is equal to n times n plus 1 over 2. Right. Now when I think about this term here, I've got the 5 over n, and then I'm adding 1 over and over again n times, right? So 1 plus 1 is 2 because I had 2 1s. 1 plus 1 plus 1 is 3 because I have 3 1s. So if I add 1 plus 1 plus 1 plus 1 all the way up to n, I have n 1s. That's just equal to n. Right, so this sum right here just returns n. Okay, I think we're a couple steps away from finishing this. What do we got? We have the 25 over n squared. I can move that 2 right there. And then I've got n squared plus n when you distribute this n. What do we have? Plus 5, just plus 5. because those ends cancel. All right. Limit as n goes to infinity. Let's distribute this. So you have 25 over 2. The n squareds cancel. Plus 25 over 2. How many n's does that have? Just 1 on the bottom. And then I've got that plus 5 over there. Okay, I think we can send into infinity. Uh, 25 over 2 just stays where it is. Oh, sorry. I'm actually taking the limit, so I don't have to carry that limit sign with me anymore. 25 over 2. That middle term goes to 0. That 5 stays where it is. So what is this? 12.5 plus 5? 17.5, I think. Yeah. Cool. So the actual true area underneath this function is equal to 17.5. Let me put that up here somewhere. 17.5. And let me get rid of this work, because now I want to answer the second part. Sketch the area. And from our knowledge of triangles, what is the area? Okay. So the function is x squared. No, it's just simpler than that. X plus 1. All right. And I wanted to find the area underneath this function from 0 to 5. Let's see. Well, that kind of gives me almost a triangle. Right? Except I need to cut off that little tip right there. So let's find the area of the big triangle. We know that the area of the big triangle, let me do this in purple then. Area of a triangle is 1/2 base times height. So the base here of the purple is, so that point right there is x is equal to -1. So that's a base of 6 times a height. How tall is that triangle? It's the function value at 5. So 5 plus 1, 6. That gives me an 18. All right, but I don't want all of that area. I just want the area from 0 to 5. Right, I need to cut off this little triangle tip. So I need to subtract the area of that triangle, 1/2 base times height. The base is 1. The height is the function value at 0. That's 0 plus 1. Gives me a 1. So 1 times 1 is 1. Times 1/2 is 1/2. So what's the area that I needed? It is 18 minus 1/2, or 17.5. Cool. You get the same thing using geometry or by using calculus. The cool thing about the calculus, though, is because I can give you a function much more complicated than x plus 1. I can actually give it some curvature, and you can find the Riemann integral.